applications of wide bandgap semiconductors, and traditional power systems analysis. We have extensive lab capabilities, including multiple simulation labs for hardware in the loop development, an electronics packaging lab, and a high bay lab for evaluating medium voltage applications up to 15 kV AC input. Together with our industry partners like ABB, Duke Energy, the New York Power Authority, and Facebook, we are leading the electrification revolution. Hopefully, everyone is familiar by now with Zoom. We have disabled audio and video for all attendees. We ask that you use the chat feature to ask questions. If you're not familiar, just hover your mouse over the Zoom window and the buttons should appear at the bottom of that window. Click chat, type your question, and we'll answer as many as we can. Note that this webinar is being recorded and will eventually be posted to the YouTube channel for the Department of Electrical and Computer Engineering at NC State. Now I'd like to introduce our presenter. Dr. Mo-Yen Chow is professor in electrical and computer engineering at NC State. He joined the university in 1987 upon completion of his PhD at Cornell University. In addition to writing dozens of publications, editing journals, and other accolades, Dr. Chow received the 2020 IEEE IES Middleman Achievement Award for substantial technical contributions and leadership in industrial electronics. Dr. Chow, the stage is yours. So make sure to unmute, Dr. Chow.
Okay, great.
Now you're good.
Yeah, thank you. Yeah, thank you, Ken, and good morning or good afternoon or good evening in your time zone. And it's great to see you through Zoom. And thank you to Ken and also Freedom Center inviting me to give this presentation. Today, I would like to talk about the Resilient Network Microgrid Energy Management System. It's research work done in our lab, which is called Advanced Diagnosis, Automation, and Control Lab, or simply ADAC Lab. So knowing that this seminar is around 45 minutes, I will state on a high-level view to discuss the issues, general approaches, and we will leave the technical details in the paper cited in the slides. If you have any question or comments, please feel free to contact me. And my email address is chow@ncsu.edu as listed on the slides. In this presentation, I will introduce Resilient Network Microgrid and the energy management systems. So I will talk about why do we need a resilient network microgrid, or how energy management system works, and also some of the technical challenges. In order to address these technical challenges, we will introduce two key technologies that has been developed in the ADAC lab. The first one is called the Collaborative Distributed Energy Management Systems, which we call it CODEM, and also the Smart Battery Gauge, which we call it SBG. We will explain how these two technologies work together to optimally and efficiently operate a microgrid. So by the end of this talk, we will present several lab scale test beds and two real world microgrid applications and how we have implemented our technology on them. So global electricity demand is constantly on the rise, as shown in the left figures, which is here. The major rising demand is in Asia. The world average electricity cost is around 20 cents per kilowatt hour. And the total energy cost worldwide in 2019 is $4.5 trillion. The figures on the right shows that the trend of different types of energy. We can see that the renewable energy will soon outgrow all the other types of conventional energy, such as coal, nuclear, and natural gas. Now, there's a lot of distributed energy resources. We simply call it DER. They are usually customer-owned or utility-owned or third-party-owned small energy resources near the site of consumption. They are usually located at the medium voltage level or behind the meter. So sometimes they are community scale and building scale. So in here, we can see in the slide DER, we have energy storage, like a battery is one of the main component, and then the battery in the electric vehicle. Now we are calling that free charging, or we can do the V2G. Is a big DER resources. And we have conventional diesel generator or combined heat and power. And we have the renewable energy is mainly wind turbine and photovoltaic. And of course, there's some like a biomass and so on and so forth. And also we can use demand response resources and many other type of DER. So in the conventional power systems, so energy resources such as 100 megawatt to gigawatt generators, synchronous generators, they are usually located tens of miles or even more from the load centers. The energy is transmitted to the load via transmission lines, then distributed via the power distribution line. In contrary, DERs are hosted by the distribution system, as shown in the left figure here, where shows the three-phase distribution circuit, the load, and the DERs close to the load. The trend of energy systems is to aggregate DERs and loads into a microgrid, as shown in the right figure. DERs enable microgrids to form islanding modes that can function without connecting to the main grid. Now let's take a look. In the United States, the number of big generators in the main grid is around like, we have around 5,000 plus huge synchronous generators. However, the number of DERs in the microgrid is much more. We can see that it's growing, and then in the order of millions and millions. The increasing number of the devices or components in the microgrid make the system very complex. In contrast with previously, we have only like 5,000 plus synchronous generators. So this poses many challenges and opportunity in this required cyber physical system domain. For example, scalability. According to the forecast from Navigance, we are expecting to see a $90,000 billion annual revenue in the distributed renewable market in 2025. This large amount of DER will result in tremendous computational burden and extremely high communication bandwidth demand. And another challenge is the interoperability. The DERs are expected to play a very important role in the retail and wholesale electricity market in the near future, which pose a lot of aggregations and integration challenges to the system operators. And their geographically distributed nature make it very difficult to observers or to observe the DER status and make timely control decisions. And also take a look of the reliability and resilience. So this is another big challenge. The growing amount of the renewable generators capacity will magnify the negative impact of the forecast error and generation intermittence. For example, the sun is not always shining or the wind is not always blowing. So the upper left map highlights the 22 separate billion-dollar weather and climate disasters across the United States. The billion-dollar events of 2020 included a record of 7 disasters linked to tropical cyclones, 13 to severe storms, 1 to drought, and 1 to wildfire. The 22 events cost the nation a combined of $95 billion in damages. So, and nowadays, also industry and government organizations are seeing more and more cyber attacks in their system. In response to the growing cyber security challenges, more financial resources that we can see from this graph are committed to tackle this issue. According to a recent cybersecurity survey, the majority of the participants has seen a continuous increase in their cybersecurity budget since 2019. So given all current challenges, a solution is to design a resilient, collaborative, distributed energy. So microgrid is a typical complex cyber physical system. So Department of Energy in US define microgrid as a group of interconnected loads and DERs with clearly defined electrical boundaries that act as a single controllable entity with respect to the grid. A microgrid can connect and disconnect from the grid to enable it to operate in both grid-connected or island mode. So after 20 years of R&D, microgrids are getting smarter and are becoming smart microgrids. In the foreseeable future, most of the components in the smart microgrids will have a controller with communication capability to talk to each other through the communication network. So let's take a look of these figures to the right. So we have a local generator, they have a controller, and then we have PV, have a local controller, and like for battery, they have local controller. For our customer, our home load, they have a microcontroller. So all those controllers, they can talk to each other, know what they need, and then provide a proper actuation or decision to their load. And this form a microgrid, and then they can also talk to the utility or the main grid together, or they can work separately. Now in the network microgrid, so this is like a network microgrid, the entire one. So the cyber layer, including the communication system, network engineering, and information technology play a crucial role. For example, the cyber layer communication topology can affect the reliability and timely delivery of the control packet to the physical layer, which is our power systems, to have a resilient and reliable energy system to serve the load. For example, in the top layer, top left figures, during a normal operation, the system level objective focus on reducing the operation cost. Thus, the microgrid will form clusters to most efficiently provide energy service to the customer and participate in the wholesale energy market through grid support point. Now, during the time of weather disasters, the microgrid will start to form their own local self-sustained energy cluster to ensure reliable and secure service to the critical load and all the feasible customers, and then they need to drop those load that is probably have a lower priority. So then we have like, for example, under contingency, we need to reconfigure the system and both in the cyber layer and physical layer in order to provide reliable and secure operation for the entire system. So the energy management in the power grid can be formulated as a optimization problem with equality and inequality constraint. So traditionally, the formulated optimization is solved in the utility SCADA system and with a large computer. The SCADA system will lead together. Let me see the animation here. Oh, no. Let me see. Okay, this is
the animation did show up. It was just a little late.
Okay. Thank you, Bharat. So this scale of the system increased from the thousands of large synchronous generators to hundreds of millions of DER. The resources needed, for example, computation time, memory, bandwidth, etc. for this centralized workflow increased exponentially, just like here, and we will not be able to. So the centralized approach will not be scalable. So let me make sure that the animation. So it will overwhelm the both communication network as well as the computers that to do those large scale optimization. Now, so what do we do? So in the last 15 years in our lab, we have developed the collaborative distributed EMS, which is a solution to the network microgrid with the advancing technology in communication system. For example, we have like a smart IoT, 5G network, smart router. So in here, let me show the animation. Okay, so on the right hand side of the figures, then we have see that each local microgrid, they only need to talk to each other and then occasionally talk to the neighbor microgrid. And then we can still achieve the optimal solution that the centralized approach can achieve. So this can improve the exponential scalability to a linear scalability, and then such that the system is easier to scale up. And also we are investigating a structured hierarchical distributed control that can further improve the linear scale to log-like scalability as shown in this graph. So all those work has been published in the papers that post at the end of at the bottom of each of the slides. Now these several figures provide the quantitative results using Monte Carlo simulation on various network topologies. So disturbance and also on computational requirement, and then also on the communication requirement per bus and the overall system reliability performance from two perspectives. The first one is the SAFE. So SAFE is a system average interruption frequency index and energy count index. And also in EENS, which is expected energy not served. Those two indices are used very often in utility. The other two measures we use is the MTTF, is the mean time to fail, and MTTR is the mean time to restoration. So we can see that both of the computational requirement and computational time in the codon increase linearly as in rather than exponential increase in the centralized control. Both SAFE and EENS improve from the centralized control to the distributed management. So we can see that the cost is reduced. So the technical details and quantitative result, and also you can find all those results and published, reported in these literatures. So comparing with the centralized solutions, the distributed solution require less powerful controllers, and the redundancy of the distributed controller is more economical and actually much cheaper. Moreover, the distributed solution does not require a fully connected communication topology. Typically, the modular distributed control is easier to maintain and upgrade. Our simulations and case studies has found that the distributed system have better reliability and resilience. Despite the chart here, that is a reflection of the table pros and cons between these two approaches. It's shown that the comparison between distributed approach and centralized approach subject to these 6 factors under consideration. So we can see that the larger area covered the better. So we can see that the distributed approach is highly preferable to the centralized approach in the smart microgrid environment. Now in here, I want to talk about FREEDM system. FREEDM that Ken has already described at the beginning of this presentation is a NSF Generation 3 Education Research Centers inaugurated in 2008 with $40 million grant for 10 years, and also has many industrial partners involved. So the central vision is the efficient and revolutionary power grid based on power electronics, high bandwidth digital communications, and distributed control, which is basically forming Internet of Energy. It allows plug and play of energy resources or storage devices anywhere and anytime. Manage distributed energy resources and storage device through distributed intelligence, and then pioneer a scalable and secure communication backbone, improve system efficiency, guarantee system stability and power quality, and support system isolated operation with 100% renewable energy. They have basic research, applied research, prototyping, and demonstration. So our lab focus with FREEDM Center, we focus on these two parts, is allow plug and play of any energy resources or storage device anywhere and anytime, manage distributed energy resources and storage device through distributed intelligence. So in this diagram, so this diagram shows the high-level description of our lab in the microgrid area that work with the FREEDM Center. We use the distributed sensors to extract system status. From the physical system, one of the lab's group is also working on building a smart battery gauge that can accurately estimate the state of charge, state of health, and remaining useful life of the battery pack. And this data will be conditioned, analyzed, and fitted into the EMS to control the microgrid. The collaborative distributed EMS has two components. The first component is the day-ahead scheduler that generates the optimal hourly dispatch commands for the distributed energy resources. While the next-day operation, the second component is 5-minute dispatch with that kick in every 5 minutes to optimize the distributed optimize the dispatch decision based on the short-term forecast to compensate the day-ahead forecast. And then the updated real-time dispatch commands are sent to the physical devices to execute. So this seminar, we will mainly focus on the scheduling problem due to the interest of time. So just a quick history of our work on this CODEM. So our basic research of the CODEM work started from 2008 with the FREEDM centers. So we moved from consensus-based distributed economic dispatch to distributed generators to the hierarchical distributed EMS for DERs. And so we have also worked on securing the network control system since the beginning of the FREEDM project. We have developed a called reputational based distributed cyber attack detection and mitigation algorithm called Neighborhood Watch. Together with the previous EMS, we are working toward a resilient collaborative distributed control system for cyber physical system and apply the technology to the microgrid applications. And in terms of technology transfer, we have partnered with Total, SA, and SunPower to work on the home energy system and microgrid EMS project. And recently we have been working with Duke Energy and NCEMC on the microgrid project. So the left figures show a typical cyber physical system. We have a cyber layer, physical layers, and we add a control layer in between. In our lab, we mainly focus on the control layer. Assume that the physical layer and the cyber layer is fixed and already reached the optimal. Then our objective is to optimally design the control layer such that the cyber physical system is efficient, reliable, and resilient. The assumption of fixed cyber layer and physical layer will be relaxed in the future. In the control layer, the microgrid control can be further partitioned into three hierarchies. That is tertiary, secondary, and primary. Primary control are mainly focused on the millisecond level fast control by power electronic devices. For example, for those motors, generators, power electronics. And then the secondary control are mainly focused on the second level or minute level system control to balance the supply and demand. This is similar to the automatic generation control. Our lab mainly focus on this minute to hour level secondary and tertiary control, which are in the energy management system domain. The tertiary control workflow is depicted in this slide. That we first forecast the load, renewable generation, and generation cost, fuel cost, and this probably can be from a weather forecasting station or from the utility, the database. Then do a day-ahead scheduling to determine the optimal operation point of the generators, energy storage, and controllable load for the next day. During the next day operation, short-term forecast that is a 5 minutes are made to enable the short-term redispatch. The redispatch optimally adjust the originally day-ahead hourly schedule and instruct the real-time operation, for example, for frequency and voltage control. Now, in order for us to design the decision, so there's we need to define cost function. The main objective EMS is to ensure the efficient, economical, and reliable operation of the network microgrid. So this table on the right shows some typical objective function for the network microgrid. And of course, different applications, they may have a different objective function. Then all you need to do is to properly formulate the objective function for your application, then you can apply our technology on it. So for example, commonly used cost function in the EMS function like electricity, import cost, battery degradation cost, battery operation and maintenance cost, state of charge, state of health estimation, error cost, reliability cost, resilient cost. So all you need to do is formulate it and then apply the CODEM algorithm on top of it. Now, there are two approaches that are typically used in the EMS. The first one is the economic dispatch, we call ED on the left, or the optimal power flow OPF on the right. So in the economic dispatch, the power system network details such as a power line and topology are not modeled. It assumes a common bus connection for all the power generators and demand. So the pros is that a simple linear programming problem can solve it, easy to model and formulate. However, the disadvantage is that the model has low fidelity and does not consider voltage and reactive power effect. So usually we use this for well-compensated system or for the DC microgrid. On the other hand, for the optimal control power flow, and that has a much more accurate model of the entire AC power system, but the disadvantage is that to solve this AC power flow is non-convex, and then we need to use nonlinear programming, which is quite challenging and from time to time. The application is usually on the AC microgrid or in the distribution systems. So we can see that in here, the inputs to the EMS, that is like a grid energy price, renewable forecast, and low profile battery state of charge. So we can send it to conventional centralized optimization approach that we have talked about, the pros and cons between centralized and distributed approach. So we can see that we both have ED and AC OPF to solve the problem. But for our CODEM, then we do this distributedly, as we mentioned before, the advantages and how to do it, and then they will provide the same global optimal solution. So let's see, here, and make sure that it's correct, okay. So now what we have done is that, so this is a cyber layer, and then physical layer, and then in between, so the controller is very simple controller. We have used the BBB, or we are used Raspberry Pi. So as shown in the left-hand side, the CODEM algorithm run on each individual microcontroller in the control layer. It costs around $50 per controller. So these controllers are located at each DER side and have control interface to the physical DER device. So as shown in this right-hand side figure, during the algorithm execution, this controller exchange its local information through the communication network configuration. And then with its label, they iteratively update its local information, use the label information and its own information to improve the decision making. So this technical detail, you can find it in this paper. So a little bit more technical details is that we use the for each microcontroller. So they implement this very simple algorithm. So it maintains its local estimation of the delta P, means the power imbalance if its own device and its neighbor, and the lambda, which is the global information of the incremental cost. So they will basically continue to work with the later through work with the neighbor through negotiation, and then the delta P, and then the lambda will converge to the global solution. So the algorithm we use is called the consensus algorithm. So all the participating agents can collaboratively estimate and iteratively converge to the same value. So based on the coverage global information, each agent can then make local decisions that are basically global optimal. Now, this we show that this is a FREEDM 4-bus microgrid system. We use this as an example. This 4-bus microgrid has 4 solid-state transformer, and now many people call it smart inverter that interface the grid, the DER, and the load. The microgrid is connected. Excuse me. So the microgrid is connected to the local utility. To us is to the Duke Energy, which is 12.47 kilovolt distribution system. And then we have bidirectional power flow at the grid connection point. And besides the grid, there are one controller power supply emulated wind DER at bus 3, controllable power supply emulated solar DER at bus 4, 3 controllable load at bus 2, 3, and 4, and finally 3 lithium-ion battery at bus 2, 3, and 4. Okay, did it move? Okay, here it is. So the internet. Now this is what happened. So this each control devices, local controller continue to talk with the neighbor and then run in the real time. So now they start to negotiate with the neighbor. Then we can see that this is for the each of the hour, 0 hour, like 24 hours. Then how should we schedule the usage of the DER? Then we can see that this incremental cost of each DER, through the negotiation process, they all converge to the optimal value. And then the power imbalance, then after the negotiation, then they all converge to 0, such that everything works out well. And then also this solution we have theoretically prove and also do the simulation and show that they obtain the global optimal solution. So after this scheduler, then we can see that this is how we should buy power or send from the grid, and how the battery each location should charge and discharge for their local load, and to maintain the resilience and reliability of the system, and also have the most economical cost for them. So this is the solution from our Coden system. This is 4 at each bus. So in here, we can see that the battery play an important role in distributed energy management system, since the solar energy and wind energy are intermittent. So we need to use the energy storage, typically battery, to work as the energy reservoir. So that's why we need to do proper scheduling to do charging and discharging of the batteries to ensure that if there's excessive energy, then the battery has sufficient room to store the energy, while when we need energy, the battery can provide additional energy. So to be able to operate the microgrid optimally and efficiently, we need to know the battery information accurately and perform the optimal scheduler. So this will lead us to—
Dr. Chow?
Yes.
Hey, we had a quick question from the chat. If you could go back one slide and maybe even one more.
Okay.
The question is, what role does the substation play? Maybe one more.
Let me see. Does it go one more? Here?
I think is the same diagram you were on. Yeah, but the question is, what role does the substation play in the architecture presented?
This is the grid. Now the usually utility often provide the time of usage, TOU, and the utility can work with the microgrid to see whether the microgrid can help them also to do their own scheduler for the utility. So it's very important. Like a utility often want to know more about the behind the meter consumption, then they can do their battery planning. So the substation is an interface between the utility. Suppose the utility is a big microgrid, so they can work together to their own benefit.
So would solid state transformer number 1 actually be within a substation?
Yeah, you can think about it that way. If you can think about the grid is one of the nodes with the rest of the other nodes.
Okay, thank you.
You're welcome. So in here, so bringing to our discussion to the smart battery gauge, which is also another important project in terms of the resilient network microgrid, and also one of the main research focus of our lab. So we have developed the smart battery gauge to provide real-time accurate state of charge, state of health, and state of function estimate to fit it into our CODEM algorithm. So the SBG get the battery data from the microgrid in real time and provide the battery status translate into data to meaningful information for the CODEM to perform probability scheduler. So this is just give us a history about our work on the smart battery gauge. To make this research possible, so we have started in 2000, probably around 15 years ago. And then also the so also NSF has start with Progress Energy at that time, and then with FREEDM, and NSF like it, and I think that is some of the technology is ready to do technology transfer, and then start to support us through several projects for technology transfer. And then in the recent year, we have been working with Duke Energy and NCEMC, and then to do technology transfer and implementation for the SBG. And now we have also expanded this to other new projects that if you are interested, we can talk more about it in the future. Now, the challenge of the current battery management systems are, first of all, usually they cannot provide real-time accurate state of charge, state of health, and state of function estimate when the battery is in use. And usually, the estimates of the accuracy will drop significantly when the battery start to degrade or age. Usually, it starts after half a year we use the battery, then the estimation of many of the conventional battery status estimation does not work well. And also it cannot interpret the estimated battery status into meaningful information. For example, after some operation, the battery will degrade in what perspective? Is that the anode is degrading, the cathode is degrading, and how does it affect the battery, and how does the battery affect our applications? So in order to accurately estimate the battery status and then interpret the estimated results, then we have developed two key technology. One is called battery digital twin, and then one is called co-estimation algorithm. So we'll briefly talk about it. This technology will provide real-time accurate state of charge, state of health, and state of function estimation when the battery is in use, and also when the battery is degrade, this algorithm can still give an accurate estimation. And then also we can provide meaningful interpretation based on the estimated value. So these several wheel graphs just showed you how challenging the battery is to do modeling. So these are papers from other people's, and then we just put it there. There's many, many papers. So there's a lot of battery is a highly nonlinear device, and many factors affecting the battery performance. This figure shows some of the characteristics such as voltage, state of charge, internal resistance with respect to the number of cycles, state of charge, capacity with temperature. So the main factor to understand the working of the battery under different operating conditions and aging factor are needed to be studied, and especially the temperature, the charging rate, calendar aging, and how does it impact on battery degradation. So in the battery is using in the real world, we need to assume that it's subject to a wide range of temperature and C rate dependent on the application. For example, for electric vehicle, if it is used in like very cold weather in like Scandinavian country, which is very different to be used in like a Florida. So all those things need to be considered, and also how fast should we charge, how much should we charge, all need to be considered carefully. So another big issue is that the data. The data is that we can see that if it takes 5 hours to get data from one cycle at a particular temperature and C rate, it takes 6,000 cycles, which is cost 30,000 hours. And then we need to get data for 7 different C rates. That is around like 210,000 hours. If we work on 5 different temperature conditions, it will take around 120 years. And of course, in industry, then they start to do parallel processing and have many testing equipment to work on many battery in parallel. But however, those costs will go exponentially high. So that is bring into why we need a battery train. So we perform our research and develop the smart battery gauge. So develop a digital twin of the battery to simulate the battery to understand the internal status of the battery. So the battery SIM battery has 2 major components. The first one is called first principle based degradation model. We call it 4DM. And then the second one is called the circuit model. So the 4DM has the ability to model and simulate battery degradation, which can be very time consuming, as we talked about in the last wheel graph. And then the TCM, on the other hand, can operate very fast, but compromise on accuracy. So we bridge this to electrochemical model, which is the 4DM, and electrical engineering aspect, which is a TCM. So we developed this a technology that uses the degradation information from the 4DM to reshape the circuit structure and parameter of the TCM. So when the battery begins to age or degrades, then the parameter of the TCM start to change. And then, however, we are not aware of how the change in this parameter affecting the performance of the battery and what we can do to optimally use the battery. So that is what the time we go back to the 4DM, and then to understand how different operating conditions affect the degradations of the battery and inform the user about battery usage pattern to extend remaining useful life. So with this 4D and TCM working in tandem, we can ensure accuracy of the model representation and then also the speed in estimating the state of charge, state of health, and state of function of the battery. So this that digital twin performance has been validated by experimental data and published data for reasonable representative battery performance and data under a wide range of operating conditions. So this is just give us a brief description of the 4DM, and then all those detail has been published by Dr. Balagupta. That is his PhD thesis. And then, so but the prominent features for this 4DM is that it's developed in layer base for high resolution, provide degradation information. So when the system start to degrade, how will affect the current flow, and then how does it affect the anode, cathode, and the separators. So give us a lot of insightful information about the battery itself.
Dr. Chow.
Yes.
We have a question. Can you further define state of function?
This is an excellent question. How about let me answer this question at the end of the presentation, because we have example to talk about it.
Okay, very good. Thanks.
But please remind me if I forgot that remaining useful life is kind of a state of function also. Yeah, excellent question. Thank you. Okay, so this is a circuit model we call TCM. Is a typical lump parameter model with some abstract parameters such as internal resistance, capacitance to describe the input-output dynamics of the battery. So this circuit is further modeled by state space to perform the state of charge, state of function, and remaining useful life estimation of the battery. So all those technical detail we can find it in the next wheel graph. Let me see here. So all those technical details are published in these papers, in those many papers. So we based on the TCM model, and then we develop the circuit model, something called co-estimation algorithm. The co-estimation algorithm has several features. We have like a regional awareness adaptive parameter identification approach, adaptive observer gain updating method, and state of charge, state of health observers. So a lot of technical details come here, and then if you want to know more detail, feel free to let me know. I will be happy to talk with you in length So just in the interest of time, I just need to move on at this time. So this show about comparison of our state co-estimations with the conventional common filter, extended common filter, and reliable, and then the sliding mode observers. So we can see that the reference is the black line, and then the regular sliding mode is green line, and then state of our one is a red line, and then the regular extended common filter is in here. So we can see that the performance of the co-estimation algorithm is outperform both extended common filter and sliding modes in terms of the two long measure and then infinity long measure, but we have a slower convergence time. But on the other hand, the common since this is not an issue because the battery application is usually a time constant in the order of minutes to hours, and then in here we are talking about the order of seconds. So these we have tested the co-estimation algorithm on many actually industrial testing procedure, including from the Samsung and Huawei's actual database. And also we tested on different like variable driving profiles. It's typical driving profile used nationally and internationally, like FTP and NEDC and all those acronyms are here, and under various temperature conditions, like from 25 degrees C all the way to minus 10 degrees C. And then we can see that the results show that the co-estimation algorithm can achieve more than 95% SOC estimation accuracy, which is fulfill the industry criteria. And all those results has been reported in those papers. So this is talk a little bit about the state of function. So that the question that can just raise. So this a quick real example is that application is that we want to know whether the electric vehicle are able to make the trip. So that is the idea. So what we want to do is then what we have done is that the smart battery gauge, we use the AI approach to predict the state of function of the battery, which the function at this time is called remaining driving range of the electric vehicle. And then for different applications, they can define their own functions. So maybe utilities say that, can I use the battery to sustain 1 hour of outages? So that is the state of function. So this is through the analyzing the state of charge, state of health of the battery, and the traffic, which the application here, the weather and the driver's behavior. So what we have done is that we use a big data approach with all those considerations: traffic data, weather data, route data, historical data, and then we train a NFIS, which is basically is a new fuzzy system. And then we know the battery, the car's dynamics. So then we, from here, and then one of the key input is the state of charge of the battery, and then the remaining useful life of the battery. So those will fit all into here, and then such that we can estimate whether this vehicle can fulfill to drive for the next 120 miles. So this is the result. Then we can see that for different like traffic, and then this is actual speed, and then that is what our predict speed of the vehicle. And then for heavy traffic, so they apparently they have different pattern, and then they will use the battery differently. So for light traffic, that's how the battery energy will consume, and then for heavy traffic, that's how the battery will consume. So we need to accurately predict in real time how the battery, the state of charge is depleting. So then we can see that that is the state of charge. Mean absolute error, state of charge, mean absolute percentage error, and then state of charge maximum error from our co-estimation algorithm. And then we map it into the function, which that whether we can make the trip or not. So we can see that we have a very good estimation error, and then we can make the trip. So this is a battery state of charge estimation. This is the state of function, whether we are able to make the trip. So hope that this provide the example that can that have answered the question on the meaning of state function. So in here, so we just show that the battery gauge in our lab that we have been developing from theory and then to prototyping to actual applications. And then we have tested in our lab, we call it Ramus DC microgrid CPS testbed. Then we have test on the 5-node microgrid system hardware in the loop. The microgrid is running in the background, and then we actually developed the use a TI inverter board to control 5 board working together and working with a simulated microgrid, and then to show the performance. And then also in 2018, we implement this algorithm in the FREEDM Green Energy Hub to show it actually work for the 3-node system for the NSF final project demonstration. And this show that we have implemented in the NCMC microgrid in the Butler Farm, and also we have implemented in the Duke Energy, the Mount Holly microgrid test system. So that's in the detail. All we need is that the algorithm is implemented in Raspberry Pi. We just need one single power supply for the Raspberry Pi, and then also, and then we tap it into the Samsung this battery energy management system through the control area network interface, and get all those SCADA system information and do a much more accurate state of charge, state of health, and remaining useful life estimation. And same things, then we do the same things with the Duke Energy in the Mount Holly, the microgrid test bed. So in here, I would like to thank you all the students that on this project that I've been working with, and it's basically a joy to work with them, and also with the current students, and also that we have several more new students just recently joined us, and they will appear in this wheel graph in the future presentation. This is the reasons in the last couple years that related publication, or last several years publication related to these 2 projects. This is some the conference papers and patents. And here I would like to acknowledge all those sponsors and our collaborators that are working with us through these 2 important research topics. And more important is also equally important is that thank you that for the audience today and your attention to attend this seminar. So Ken, I pass the ball back to you. Any questions?
Great. Yes, we do have several questions. First, could you back up 2 slides to show the page of references? I know that we had a question from someone, where could we read more about this research?
Sure. And all those papers are listed in my website.
Okay, perfect.
In my webpage. And also, it's better yet, go to the ADAC website. ADAC website, if you Google ADAC, NCSU, then they are there. So it includes much more information than my website. But yeah, with both publications are listed on my website and on the ADAC publication website.
Okay. Okay. So if attendees, if you want to take a screenshot of this, that would give you a good starting place. But I agree. The website for ADAC is also a good list of resources. We had an earlier question. Can you name the best software for simulating DC microgrids, and specifically for looking at protection for DC microgrids?
That is not a good. I don't really know the answer. I don't know whether probably yes. I'm yeah. Please chat with other faculty or utility. I'm not familiar with that.
Well, and I had actually chatted with Dr. Balagopal as well, and he pointed out that your team uses OpenDSS as well as MATLAB Simulink for a lot of your work, and I know that the question, my response to the question as well, was it kind of depends on the application. But OpenDSS is freely available software through the Electric Power Research Institute. Is that right?
And PSCAD, all those, but I just simply I haven't used them before. Yeah, we mainly use a Simulink. I think my student they use OpenDSS. Yeah, correct. I don't know whether Zheyuan is here. He used it a lot, and yeah.
Okay, and I would say too that the references will include specific cases of which software were used for simulating some of the microgrids.
And can OpenDSS is FREE, yes.
Okay, good. Thank you, Barak. There was another general question about, hang on, let me scroll back to it. What are some of the remaining significant challenges regarding cyber-physical distributed energy management?
Oh, many, a lot. I just name a few. For example, how do we configure the cyber layer to work with the physical layer together? Because right now we have only talked about the control area in terms of a consensus network. But there's a lot of things tied with like how fast the data will come in, how fast we can make decisions. And yeah, many of these issues in addition to the scalability and interoperability to make it more and more efficient. So I think I make sure I understand your question properly. So some students say, researchers will always say that is sometimes industries say that if it's good enough, then it's good, right? And then but research always want to say, hey, can we do better? So, but those distributed control people start to using it. So, and this, so that's why NSF encourages us to do technology transfer. But in order to further continue to do optimal one, then it's much more, a lot of research can be done. So I don't want to give a wrong idea, say, oh, is it not ready yet? No, I think it's ready to be used.
Okay.
But many things continue to be worked on. Yeah.
There's still a lot of things you can do to optimize the system.
Yeah.
Certainly. Well, and this question is sort of related to that, and I'll just read it. Based on results provided in recent publications from you, Dr. Chow, more than 2,000 time data exchanges between all agents, buses, are required to receive optimal operation solution in a ACOPF in a 22 bus test system. And the question is, I wonder how this is capable, how the system is capable to handle the huge data exchange in real-time operation.
Yeah, so 2,000 something is not really large because suppose like we talk to each other like 10 times a minute or 100 times a minute. So just locally, because it's not globally. So it's just locally several people communicate, and then only usually it takes around less than 10 minutes for us to do all the scheduling. Yeah, we have many devices. They just communicate, just like what we are talking right now. So yeah, 2,000 iteration is not large at all.
So even though it seems like a big number, it's actually not.
Right. And also each group, they do their own talking. Each group is only 2,000. Each device, like we are running at like a megahertz, the controller.
Okay, good point. And then I think this will probably be our last question because we are a little bit over time. We got started a little bit late, so that's okay. What challenges were faced for physical implementation, for example, in Mount Holly?
Interoperability. So, so right now there is no standard yet. So that is, but we bypass it. So we use a Raspberry Pi. So we still have a function. They have a device by themselves, like a controller and SCADA system. We tap the SCADA system into our device, and when we make the decision, we send the output to the actuator. So that's how we do it right now. In the future, if this technology become like one of the standard in the industry, so what I think they will do is that for all those devices, then they have a built-in function. They just connect with each other and then start to negotiate. That's how I see probably in the next several years, that's what they will do.
So interoperability, I agree, is yeah, a major barrier. And it sounds like we're not quite yet to true plug and play. Despite, I mean, that's our goal, right, is for the devices that we build, certainly within FREEDM and within your systems, is to, you know, make sure that these things can just join the grid, recognize each other, and then be able to operate as a system. But not quite there yet. Yeah. Well, Dr. Chow, thank you very much for your time today. We really appreciate your presentation. Thank you to everyone who joined us. And like we said, this meeting was recorded, so we will post this to the Electrical and Computer Engineering YouTube channel very soon. And we thank you for your attention, and this will end today's webinar. Thank you.